We're talking about the ideal gas law, and so we're dealing with three major factors here. We're dealing with pressure. Pressure is the force that a gas exerts upon a surface divided by the area of that surface. It is a statistical thing, as talked about in a previous video. We're talking about volume, is how much space this gas takes up, and we're talking about temperature, which is a measure of how fast the particles are moving. Basically, it's the average kinetic energy of all the particles. Now, there's various approaches to this. Traditionally in class, I just jump straight to the ideal gas law. Chemistry teachers tend to start with Boyles Law, Charles Law, Gilles Law, and for the sake of this one, I'm going to start out with the other ones and sort of work myself into combined gas law too. Work my way into the other one, into the ideal gas law, which basically sums it all up beautifully. And I happen to remember it personally. Which one's Boyles Law? Which one's Charles Law? I cannot regurgitate which one is which. To me, they all blur together. Ideal gas law covers it all. However, Boyles Law, just for the sake of completeness here, Boyles Law, sometimes called the Boyle-Mariotte, pronounce it better yourself, law, basically is relating pressure and volume. P is for pressure, and V is for volume. The fact that the pressure and volume are inversely related. Now, this assumes that everything else is held constant. So if I hold the temperature constant, so imagine a balloon filled with a gas. If I hold the temperature constant, so the particles are still moving around at the same speed, that I've got all these particles bouncing around. And so now if I make the volume smaller, well, if the particles are still bouncing around at the same speed, that when they hit the wall and bounce backwards, the same force is being applied to them. So since pressure is force divided by the area, if I have the same force being applied to the particle, to this ideal gas molecule, that means that, well, if area drops, pressure has to increase. So as volume gets smaller, the pressure goes up. So imagine this way. Imagine that you've got 20 people in a classroom and the walls start getting smaller. Think Star Wars. As the walls are getting smaller, now you're moving around in the classroom. Each of you represents the gas molecule. You're moving around in the classroom. As it gets smaller, well, if you don't slow down speed, that means you're going to be hitting the wall more frequently. As you hit the wall more frequently, that means there's going to be more force being applied. And so that's another way of looking at the fact that pressure is going to be going up. So Boyle's law is the fact that pressure that's the proportional symbol. Pressure is inversely proportional to the volume, inversely because it's 1 over V, not just V. So as pressure goes up, volume goes down. And actually, from that point of view, no, we're going to leave it like that. So next one is Charles' law. It's like the volume and temperature are the same. So imagine again, I've got this balloon here with gas in it, and I turn up the temperature. Now, if the pressure stays the same, and that's the harder one to actually, if you actually try to think through this, if the pressure staying the same, well, the balloon's going to get bigger. That's the essence of a hot air balloon. You put hot air into it. As the temperature increases, the volume increases. Now, the pressure is all on the inside should equal the pressure coming from the outside because we want equilibrium there. The balloon or whatever you're inflating is always assuming there's some adhesive forces involved also. I didn't want to get down that path. But the very crude version of this is that the pressure inside must equal the pressure outside. That's equilibrium. And so as you increase the temperature, the volume will increase. Now, if I take a balloon and I just somehow increase the volume, I get sticky fingers on a balloon and start pulling outwards, and you're thinking, how's the temperature increasing? The deal with that one is that if I just grabbed a surface right there and could somehow just expand it, I'm not necessarily going to increase the temperature, but I'm also dropping the pressure. So Charles' law assumes that the pressure stays constant, and that's the difference. If I'm actually physically pulling it apart, then the pressure inside does not have to equal the pressure outside, the air pressure outside, because I'm exerting an additional force to the problem. So Charles' law, volume and temperature are directly related. Now the last one, I've always heard called Gilles Law. I assume he's French, and that's why it's pronounced Guy. Excuse me. Pronounced Guy. But it also, according to Wikipedia, it's also called Amontons. That's Amontons. Amontons law. The fact that pressure and temperature are related, and that assumes volume stays constant. So again, if I have a balloon here, and somehow I could fix the size of it through magic, that as I increase the temperature, the particles inside are going to be moving around a lot faster, which means when they hit the side, it's going to require more force to bounce that particle back in, and that registers the greater force, greater pressure. That's the relationship there. Now, taking these three laws, we can combine them. The fact that we have pressure and volume are inversely related. If I multiply both sides by the volume, I get pressure times volume is proportional to some constant. We have the volume is proportional to temperature, and we have pressure is proportional to temperature. Well, this is sometimes brought together in what's called the combined gas law, the fact that the pressure and volume are inversely proportional to each other and both proportional to temperature. And so PV over T is equal to some constant. K just stands for some constant. Now, if we take this one, what is that constant? Again, it's an ideal gas. And so we come up with this nice little relationship right here, where pressure times volume is equal to this. This is the number of moles of gas, and that's moles is an SI unit, it's metric, SI unit for the number of particles. Times this gas constant right here, times the temperature in Kelvin. So PV equals nRT. That is the magic of the ideal gas law right there. It's all those other ones put together. Now, what makes a gas ideal? What it ignores, the biggest thing it ignores is it ignores that the fact that molecules might run into each other, and therefore it also ignores the fact that they have any size. These particles assume only hit the boundary, and therefore it can be derived. If I make it ideal enough, you can come up with something like that. Now, there is a version of this where that takes into account the size and the fact they interact with each other, and that is called the Van der Waals gas law, something like that. I'm flashing back a couple of decades here when I first learned that terminology. It's a chemistry thing, so it's obviously not as important as the physics aspect. But ideal gas law, PV equals nRT. It's very useful for those who do that kind of stuff.